Okay, let's begin. So, yeah, last time we have covered part of this slide, and we have seen that what is a network core, network edge, right? And we also have seen the different digital media to connect to the internet, right? So like you can through DSL, you can through the through the cables, TV cables called H, HFC, right? So, and also we can, let me see, we can using, the home network, right? So you can actually have a net where you have some internal IP, but you actually only require one IP out of your house, okay? And so these are the devices, okay? And here, this is institutional network, right? So we have like the UAB, and there's a lot of machines inside, but we have the institutional link to the ISP, right? And the router, right? Institutional router outside the UAB. And we also see a wireless network. We have the LAN, wireless LAN, like within a building, within a room, okay? And we also have the wide area network like 4G that we are probably using these days, okay? Which have a base tower, and because of the radio signal, it can reach very long distance. And so also, next we talked about this page, right? Basically, we talked about the concept of packets, right? How they are transmitted. And we know that there is a speed that you can put a packet onto the wire, right? So this decides like the expense of the device, right? So faster, of course, the more expensive, okay? So this is called the packet transmission delay, okay? So, you can only put so many bits into the wire per second, okay? And we also talked about the physical media, right? So that I think in the lab you already see how to, connect devices using different kind of media. I think there's a particular, button, some links that will help you choose the best link, right? Automatically, but you need to understand those different kind of links, okay? What they are, and how they function, okay? And these are continue of the link, and so. Today we will continue with especially the math part of the mathematical computation part of the computer networks. Okay, this is a very basic mathematical computation, and we will have a quiz released today on that. Right, so basically you will have a on each router you will have a queue. Let's say in this router we have 5 packets, right? We can hold 5 packets in the queue, okay? And those colored are the packets that are already, already filled with concrete content, okay? These are empty space where you can hold 3 more packets into the queue, okay? And this particular packet is being put on this wire. But we know that because the packet has certain size, how many bits, right? You cannot just put it on the wire immediately, right? There's every second you can put so many bits, right? So there's a certain time that you need to take just put this packet into this wire, okay? And then also a propagation delay, which go from one end to the other. But that's almost light speed, so that time oftentimes can be ignored unless you are sending from West Coast to East Coast or sending overseas. Okay, we will see the details in the next few slides. Yeah, it's putting the packets to this line, okay, to this line, right? So we have a wired connection and a wireless connection. You are putting to the medium, basically. Okay, you can also, there's also speed you can put to the air, right? So here in the router, it's always, wired connection. Okay, you are putting, I think a student asked, so there are a lot of bits here, right? You can only put these bits into the wire at a time. So it will take some time to put the whole packet onto the wire, and then it will propagate that way. Okay. When you put to the other side, it also takes some propagation time. But this is light speed. But how fast you can put bits onto the wire, there's another speed, right? Okay, this is transmission speed, right? So it will be, this will be the bottleneck. How fast you can put bits onto the wire. Okay, the transmission from one end to the other, it's light speed, okay, very fast. And there's one thing that you need to take care of, right? So the packet, so previously those slides we have covered, so I go really fast, okay? From this slide on, I will go a little bit slower and go into more detail, okay? The packet arrival rate to the link, right? So so the first one is saying that if you have more packets than what you can hold. For example, now we have 3 slots, right? 3 more packets we can hold. If then we have 4 packets coming, and this packet is not already put in the while, but 4 packets already coming, right? But we only have 3 slots, then we have to drop a packet, okay? So if, you know, the arrival rate to the link coming inside is faster than what you can go out, right? Then it will, these packets will pile up in the queue, okay? And so that's why we need a queue in the router. So it allows temporarily, sometimes you have some high-speed incoming packets, then outgoing, okay? It will pile. But when the speed slows down, then it will clear. And then so the queue is like, hey, now my incoming speed is higher than outgoing, I will pile. Then suddenly, you know, there's not much packet, it clears up. And then suddenly there's another peak, right, I pile. But if you go beyond this packet, this capacity, my router cannot hold so many packets, it will drop, okay? So this packet will not be taken into the queue because there's no space. This is the packet drop. You will see that later, okay? So we need a buffer to allow this case, right? The link, you know, the incoming rate will temporarily be faster than the outgoing link rate, okay? Right, then, for example, we are still putting the packet into this while, which will take a few, maybe milliseconds. Then these packets come, right? 4 packets come. Then I cannot clear the head space for it yet. Okay, and then packets queue is waste for its time. Right? So there's also queuing time. Right? For you to be move to the head of the queue and put it on the wall, all the other packets before you should also be cleared first. Okay. So again, this packet is being transmitted, which means it's putting on the wall. Okay. And these 5 packets. These 2 packets are in the queue. There are 3 slots that can hold more packets. Okay. So there's also a delay because once you arrive at the router, you are not immediately putting it on the wall. You still need to wait till the packets before you in the queue are put on the wall, and then it's your turn. Okay. And yeah, this is the free space as we discussed. But if there's no more free space, right, it's all colored, for example. Then if a new packet comes, it will be dropped. The packet. So overall, you can think about the time where you pass each router cause some delay. But this delayed time is called a nodal delay. Okay, nodal means this node's delay, right, passing through this node. Right? Of course, if you have multiple routers, it's a summation of this nodal propagation time. Okay, and we will see something today. Okay, to clarify. Okay, I think it's in some later slide. Okay, so we will see how if you pass multiple routes, right, the time at each router will have some delay. Okay, so you will pile them up. You will sum all the delays. That's how long it takes from one end to the other, right? How much? I mean, yeah, how much time it will take. Okay, so yeah, let's take a look at what is the nodal delay time consists of. Right, there are 4 parts. Okay, and I want to emphasize again, this transmission delay, transmission time is the major bottleneck. How fast you can put the packet onto this wire. Okay, and you know, so this actually depends on the device, that is the router, right? How good it is, right? If you buy a very expensive router, it can put on the wire very fast, right? 10 Gbps, 100 Gbps, right? Even many hundred Gbps, right? Backbone router, I think definitely needs that speed, okay? And also for your Ethernet switch, right? Maybe it's 1 Gbps Ethernet, some are 10 Gbps Ethernet, right? So how fast, this is the major bottleneck. How fast you can put it on the wire is a major time-consuming part. Okay. Another time-consuming part is the queuing delay, right? Especially, this is the automated control because a lot of people are sending through the route. If other people are sending a lot of traffic there, then maybe your packet has to be dropped, okay? And hopefully everyone is following some protocols that they will back off the speed a little, right? So this queuing delay is, so these 2 are the major costs. Okay? One is queuing delay caused by congestion. Okay, another is transmission delay decided by the device. Okay, what are the other 2? Right, one is called processing delay. Okay, nodal processing. Why we need processing? Because when the packets come, we know that when, for example, when the packets go here, maybe some electric signal will flip a bit, right? Then there will be some error, right? We need to check the error. If there's an error, we need to notify a retransmission, okay? So this thing itself takes some processing costs, right? So there's some CPU internally in this router do these things, okay? Or processing units, okay? And so again, in this example, of course, we only have this outgoing link, right? Maybe we can also go to this link. We already have two, but in the backbone, maybe we have another router here. So we need to look up the, routing table. And if you want to send to the destination, which is the next router, this router or this router, and then I put onto this one, right? Before you put on this one, causing the transmission time, right? You first need to compute which link I need to do. I need to do this, right? So this, routing table lookup also takes time. So there's some processing costs like CPU time here. Okay, but this is really fast compared with the network transmission. Okay, so sometimes we can just ignore it. Right? Another part is a queuing time, queuing delay. This is the time we wait for the output link, wait at the output link for transmission, right? So because here actually the queue is built something like this. Each output link they have a queue. Okay, like to this router we have a queue, to this router you have a queue, right? And when you come, hey, I decide to go this route, I will put into this queue, okay? But what if, for example, when you come, right, there's no packet in the queue, then I will directly put your packet onto this link, okay, this one, okay? And then you have no queuing delay, right? It's almost zero. But it's also possible the queue is maybe already very, very, very full, right? So there's still space, so you are not dropped, but there's a lot of packets before you, right? Each packet will take some time to put into this link, right? And then there's a lot of queuing delay here, right? So you have the queuing delay. And interestingly, if you look at it, the queuing delay also depends on the transmission speed, right? So if you have 5 packets, and each packet needs to take some time to put to while, like T, then you have 5T of queuing delay, right? After that, you have T time of transmission delay, assuming all the packets have the same time to send, okay? So this is queuing delay, which means when you arrive at the queue, you need to first get these things sent out, right? But each packet needs to take some time to put it on the wire, okay? So you have to be queued. Now, after you move to the top of the queue, right, to the head of the queue, right? Now it's your turn to put on the wire, okay? The time is the transmission delay, right? So this transmission delay is really, when you think about transmission, you think it's transmission from here to here. No, here when we talk about transmission, it's really the speed, how long it takes for you to put on the wire. Because we think the propagation is light speed, really fast, right? After you put on the wire, it's done, right? So something like this, but we still need to account for that using propagation delay later. Right now, we're talking about transmission, okay? So the transmission delay depends on 2 things. Firstly, how large a packet is, right? So if you have like 4 KB or something, right? So how large a packet size you have, okay? And then how many bits you can put on the wire per second, right? So this is the speed, how fast you can put a bits on the link, right? And this is how many bits you have. So then the transmission delay, the transmission time it takes to put so many bits on this wire is the number of bits divided by bits per second. This is a second, maybe 1 millisecond, 0.001 second, okay? So this is a major bottleneck. And that's how maybe you buy your switch, you buy your Ethernet switch, for example, you buy your wireless router, you buy this, or the ISP buy their institutional router or the backbone router, right? So they need to pay higher to get faster speed for transmission delay. Okay, transmission delay also affects queuing delay, right? Because if you are here, all the packets before you take some time to put on the wire. And that speed is do this R. Okay. Right. And finally is a propagation delay, right? So although we don't really need to care about it, but if it's for long distance, right, from abroad, right, to over the ocean, right, so then you need to definitely consider this, right, because the light still have some speed. Light speed is 3 times 10 to the power 8, right? But because this medium is not like a pure empty, right? It's a metal, right? So there's some decrease of speed. It's usually 2/3 of the light speed, okay, but still very fast, right? And depending on how long your link is, right, and the speed it transmits on the link, right, it will take some time to arrive at the other end. But that time is really fast. Okay, this is your link length, right? Okay, this is time, okay, per second. This is speed. Right? So this is the link length. Let's say this can be pretty long, okay, from US to China, for example, this will be a very long distance, okay, and then you have S, right? So S is a propagation speed, light speed. Right? Even it's very fast, but there's still some time, okay. But when you just need to add one propagation speed, because if you put in this Y, this reaches the other side, right? The other put on this Y will consecutively follow you to reach there, right? So really, the first packet is the time you need to compute, right? This is the delay. The other packet will follow. Okay? So you don't need to add so many packets of the delay. Okay, it's like the other are just accounted by queuing delay. Any questions? Yes, this is probably very important because you will have quiz on this, right? So you need to understand. Okay, so one important concept, the transmission delay. So you have a concept of bits per second, how fast you can put. Okay, and because a lot of people besides you can send stuff, right? So this queue can queue up. Okay, because it's incoming speed is faster than outgoing speed. Okay, but in that case, again, this are important, right? This depends on how fast you can clear those packets before you, right? Okay, I see a question in the chat. Okay, I see a question asking to explain the transmission delay again. Okay, right. So let me give an example. For example, this guy has 10 bits. Right? Usually it's way larger. Okay, 10 bits. Okay, this packet has 10 bits, and we know that the router can only put onto this link 1 bit per second. Okay, and it will take 10 seconds. Right? It will take 10 seconds. This thing will be 10 seconds to put this packet onto this one. Okay. After that, I will put this 10 seconds, 10 seconds. So if you are here, you need to wait for 30 seconds. This is 20 seconds, this is 10 seconds. Do I answer your questions? I think a student asked. Yeah, I hope this is clear. Okay. Again, the numbers are not meaningful. Okay, so just to make sense clear. All right, so next, let's look at the queuing delay. Right? So queuing delay is kind of something that it's out of your control. Right? It depends on how fast other people are sending that is sharing this router. Okay, so there's actually a relationship, but this is based on a mathematical theory called queuing theory. So we don't want to touch that. Okay, but there's some conclusion that you can understand. Okay, so here are let me see what I have to. Here are the conclusions. Okay, firstly, so as I said, we have a rate, right? The link bandwidth, how many bits you can put on the wire. Okay, and each packet itself has a certain size. Right? It's not a bit. When we say that we want to bundle the bits to packets, but we have a maximum size. Otherwise, it will occupy the whole wire all the time. Other people cannot send their packets. Okay, and there's another thing. Right? So average packet arrival rate. Okay, what does this mean? This means how fast packets are coming into your device, for example, your router. Okay, so if we look at this, then we have these conclusions from queuing theory. Okay, so firstly, you can see we are comparing LA divided by R. Let's see whether that one. Right? So basically, we are comparing which one is larger, LA or R. Okay, so if you look at here, the LA is what? So this is saying, hey, this is average packet arriving rate, right? Which means every second how many bits arrives. Okay, and how many packets arrives. Okay, and this is a packet length, L. So for example, every second I have 2 packets arrives. Each packet is 10 bits. Right? So then we time together. Every second I have 20 bits arrive. Okay. Then how many? This R is the link bandwidth, which means how fast I can put my received packets onto the wire. Okay. If this is 20, that means incoming number of bits and outgoing number of bits is the same. Right? Then it will be equal to 1. Okay. So when the ratio will be 0, this means my incoming bandwidth is a lot lower. Right? So for example, this is instead of 20, maybe just 2. Or we say if this is 20, our outgoing bandwidth is 200. Right? So then this is close to 0. Okay, what is 1? If this is 1, then it means that your incoming speed is higher than outgoing speed. Okay, so what will happen if this rate is like this for a long period of time? Okay, Firstly, if your link bandwidth, like you buy a device that can put bits onto your wire very fast, very fast, much faster than necessary, right? Because the packet comes so many bits per second, okay? But you can put a lot more bits to the wire. So this is very close to zero, okay? If that is the case, right, this is close to zero, very far from it. Just almost no queuing delay, okay? You can prove that. Again, we're assuming this rate, arrival rate is like this, but there's randomness, right, for like Poisson distribution, okay? Right. And so this is one end. Okay. Another end is what if my incoming speed is always more than my outgoing speed, right? So if that's the case, the average delay will be infinite, right? So you can think about it. Maybe the first packet will take some time, right? And after a while, the queue will be filled up. Okay. Beyond that, all the packet will be dropped, right? And then retransmit. So this will be infinite delay. Okay. So I see another question. What's the unit for traffic intensity? What do you mean by intensity? It's just a bit per second. Okay, this is the unit. Okay, how many bits per second? Okay, here A is we are saying how many packets per second arrives, right? And then we times the number of bits per second per packet. Then this is how many bits we receive to this router each second. Okay, this is how many bits we can put on the wire to leave per second. Do I answer your question? Okay, okay. So of course, if your incoming speed is larger than your outgoing speed, then you have a queue that's passed up forever until it it overflows, right? And then packet drop. So you will basically, after a while, your packets will never be delivered. Okay, just infinite delay. Okay, as we show here. Let me go through. I don't know why. Let me try. Yeah, it's infinite delay. Okay, here you can go infinite. Okay, this is infinity. Okay, and another thing is that what if we are close to one, right? Close to one, you are already going to infinity. Okay, beyond one, it will just be infinite. Okay, infinite. Right. So, what does that mean? So that means even if your incoming speed and outgoing speed are balanced, right? That's not good enough because you can frustrate, right? So it's called Poisson distribution. Sometimes, sometimes maybe it's idle. Sometimes it will be overly, more than the queue capacity. Then you have some packet drop. But the overall effect will be that your delay will be very long, and it shoots up. Okay, while your incoming rate is very close to the outgoing rate. Okay, while your incoming rate is very close to outgoing, your time will increase very fast until almost you are equal. Then it goes to infinity. Okay, so what does that mean? That means your device that serves a lot of other downstream, maybe you can call it upstream clients. Okay, maybe this is the backbone router. These are the households. Okay, or maybe this is our Ethernet switch in the lab room. Right, these are your lab computers. Okay, so this guy should be over budgeted. Right, so so it should be over deployed. The bandwidth should be way larger than the actual need that you will use, the peak bandwidth you will be using. Okay, so put simply, you want to add this sweet spot, right? There's almost no queuing delay, right? But if your budgeting is maybe 20% of 5 times more than what you need, you will have no queuing delay. But if it's just half of the what you need, you will have some queuing delay. If you just budget for what you need, it will be very long queuing delay, okay, unfortunately, right? So you do need the backbone service to have much higher bandwidth than the total bandwidth that is required. Okay, the bandwidth means the speed, okay, how fast you can put on the wire. Okay. All right, so this is the concept, and this is the conclusion from queuing theory, right? So you can actually prove that. Any question? If not, let's continue. Okay, so here you can see. So this is a example, right? So previously we just talked about for each node, right? Each router, for example, you will have some delay. So what if you have a total router, right? So for example, here we have delay of 2 seconds, 2 seconds. Again, it will be milliseconds instead of seconds. Okay, I'm just using some, makes things easier to discuss. Okay? So in that case, the total will be summation of them, maybe 10 seconds. Okay, so that's why router will try to find a route that passes less routers or with less delay. Okay, so that's the route detection. So that's the initial phase. You don't want to send it through a very time-consuming route. Okay. So how can we see, for example, is there a way that we can see what are the internal routes and how long it takes for each packet to ride that route and then to the next route, etc. Right? So actually, your computer is already equipped with some tool, okay, so called a trace route program. What it does, it will provide delay measurements from source to destination route. Okay, and we will see something. Okay, so how it implemented. Actually, it is in the protocol. There's a field that you can put. Say I can pass at most how many routes. Okay, beyond that number of routes, I will just think I'm failure. I don't continue. Okay, so let's say. So this trace route implemented by the packet, right? So we have a say max hop 3, okay, 3 hop. Then I go to here, and the packet will minus this max hop to 2, okay? And then I go to the next, I minus the max hop to 1. And then I go to here, the router finds, hey, you minus to 0, I should not continue forward. I will just send it back, say, hey, it's failure, right? Then you can get exact time it takes to get the third router, okay? You can control this number, sending different kind of packets with different numbers to probe all the routers until you reach the destination. You can increase one at a time. Okay. Yeah, it's like ping, but you can control how many intermediate routes you want to pass. Okay, you don't want to go on if that particular number of maximum hops allowed is passed. Okay, so we'll see that field later. Okay, but for now, I don't want to add too many additional stuff to you guys. Just to keep in mind, there's a way to implement it. Okay. Right, this is basically the network layer. Okay, we will see. And so here, what it does is that the trace route will for all I means for the first router, second router, third router, this is the ith router. Okay, for all possible I, right, you increase until you reach the destination. Okay, you will send 3 packets, which means you send 3 packets to 1, then 3 packets to 2, and then 3 packets to 3. Okay, on the path all the way to destination. Okay, right. And the route I will return packets to the sender, right? Because max hop to reach, I don't forward it again. I say failure. After so many hops, I still cannot reach the end. Okay. The original goal of that field is to avoid the infinite loop of the routing. Okay. Something must be wrong. It's a error control because you don't want to have some issues with the routing, right? So packet should be consumed at some point in time. Okay. Like either by the end destination, but if you have so many hops still cannot be consumed, you should cleanse it, okay? Tell the end, hey, I cannot divide. I just eliminated this packet. Otherwise, if you have some packets that can go on forever, you can attack them. Just send the packets and to some destination, but that does not exist, or keep routing back and forth by attacking some routes. Then you will have all kinds of packets generated but not consumed. Then it will cause congestion. So that's the original purpose of the field, but it's utilized by the trace route to just detect all the routers and send the stuff back to you. Okay. Importantly, it will send how much time it takes from this link to this link. Okay. From round trip time. Okay. So the standard time intervals between the transmission and reply. Basically, you send all the way. Hey, that the hop number is reached. I receive. Right. So this is the time. But for each router, we will send three packets because the time can fluctuate, right? Because this time when I send this packet, this guy is busy, right? There's a lot of packets in the queue. Next time the queue is clear, it's faster. So in order to get a relatively stable time, 3 will be sent and 3 such interval will be reported, okay? So here's an example. We have 3 probes and then 3 probes, okay? And this is what we will see in the result, right? So for example, you want to connect to UMass, right? From UMass, right? Maybe right now this guy is in UMass and connect to this France destination, right? These are the routers along the way. What are the routers, right? So you can see some goes to France already, some are still maybe US, right? And you can go into somewhere somewhere in the middle, okay? Right, so, and you can see the time. which generally increases, right? So 1, 2, 5 increases because it's farther and farther away. You pile the time around, but there's some frustration because each time you send, the condition different. Right? Sometimes you send maybe it's very congested. Sometimes you send it's very light. Okay, that's possible. Right? So it's in time estimate. Right? So we can see this thing functioning. Let me see whether we can. At least on Mac, trace route is by default already there. Okay, let's take a look at this. So this, I'm not sure whether you can see it clearly. Let me make it larger. For example, if I want to do trace route, right? So I want to go to Google, okay, google.com. Right, so you can see here, I'm going through these routers. Right? This is actually internal, right? So the 192 and the 168 is internal, okay? And then it goes to some other routers and all the way finally reach maybe Google, okay? And some router intermediately may ban you from reply. Okay, it will not tell you anything. Right? So because this is, I think, ICMP protocol. Some can, like they have firewall, they don't let you know. Okay, they can ban you at certain point. Okay? But most of the router will just reply you something. Okay? Yeah, then we reach the destination. Okay, this is a last router to Google. Right? And we can also try, for example, UAB. So it will be similar, but through different routes, right? Okay, so yeah, so I think it will take some time, maybe. Okay. So yeah, but it's something like this. Okay, so this maybe reach some UAB internal IP address, right? So and this it's interesting. They go to different machines in this, so it's 3 lines. Okay, I don't know why, but different times it's go different. This is extremely long compared with the other 2 times. Okay. And this refuses to report to your trace route kind of packet. Okay, so there's some firewall maybe. Yeah. So that's basically how you can observe stuff. So there's no response, right? So you can see when we get to here, we wait for a much longer time. The reason is it refuses to report to you, right? It's like there's a firewall, right? But it may not be firewall. It's just a inside the device. There's some rule. I will ban that protocol. Okay. And if that is the case, then it will not reply to you. But it will take some time for you to detect that, right? You need to allow it to reply, let's say 1 second. After 1 second, I still have no response. I assume this is happening. That they filter out this packet, right? And if that happens, then you will see star. Okay, and you can see usually some sudden jump in time, right? So for example, here, this is still within US, and this is in in Europe already, right? So this is transatlantic, right? So then suddenly we have a sudden jump in time because maybe some fiber over the ocean, right? So you can see something if you connect somewhere abroad. Okay. Any questions? Okay, if not, let's continue. Right. All right, so now we reach the concept of packet loss, right? So we know that we have a buffer, right? Here in this example, all buffers slots are filled, right? So these are the waiting area, but there's no more place for you to wait. But you have another packet comes, right? What can the router do? It can just drop your packet, okay? And you have to retransmit. After some timeout, you will find it and you retransmit again. Okay, so the router has no bandwidth to respond to you or handle your stuff. Okay, and this is happening if you have congestions. Okay, and if your incoming speed is always larger than outgoing speed, this will always happen, right? So that's why your delay time will finally reach infinity. It will always be dropped. Right. So the buffer has a finite capacity. Okay, and the packets arrive to a full queue will be dropped. Basically, the router will refuse to process it. Okay, and the last packet may be retransmitted by the previous node. Okay, or it may say, hey, I don't handle the retransmission with the previous device, right? Maybe between 2 routers, I don't want to handle it. Then your end device, end system will have to handle it after some timeout. hey, after 1 second, you still didn't deliver the packet. Right? I assume it should be delivered in 10 milliseconds, right? So I think it failed at retransmitting. Okay? And that's why we need a congestion control, because if everyone is retransmitting, right, you will generate a lot of packets into the traffic, and there will negative impact, right? Right. So because of the packet loss, you transmit more, retransmit, there's more packets, that cause more loss, etc. Right. That's why we need TCP, the congestion control protocol for them. Okay. I see a chat. Oh yeah, so we will discuss the socket after this slide. Okay, so because these concepts I think is very important, so I put it here first. Okay. Right. So now we have the throughput. Right. So the throughput is how fast, right, you can put into one cent to the other side, right? Bits per second, as we said, right? Bandwidth, throughput, and you know, speed to put on the wire. It's the same thing, right? When you think about bandwidth, it's really the bandwidth per second, right? It's by the time, okay? And okay, so let me see. So there are two ways to measure the, you know, the throughput, okay? Because if you, let's say if you use some P2P software, right, you will see some small window there tells you, hey, they will report two things. What's the instantaneous throughput, right? And what is the average throughput, right? So there were two numbers, how many bits per second, okay? So what's the instantaneous, right? So this is the current time point, right? The one point in time, right now, right? Maybe there's still some small time window, but they're really small. Okay, it can be think of it's like right now. What's speed? Okay, right. The average means over a long period of time. Let's say we have a sliding window backwards for 1 minute. What's the speed for the recent 1 minute? Okay, right. So this is the average speed. Right, you will usually see two speed when you use some software to download. Okay, so this is the concept. And what decides this speed or this rate or this bandwidth? Right? We use R because it's more like a rate. Okay. So, for example, if you think about it, right? So if this device sends it through a narrower bandwidth, you know, link, and then this outgoing link is much faster speed. Right? Where's the bottleneck? Is this useful? The answer is no. Okay. So because this already control your flow speed. You just think about the pipes and the water, right? If you can only get so many water in and out, so even though here you have a much wider pipe, it's useless, right? You still can get those. Okay. So a short answer is that if you have a path through many routers, right? The bottleneck link will be the link where this speed is slowest, this throughput is slowest. Okay. Yeah, the next few slides are just describing this step. So we assume a simple case, we only have two links, two pipes, and one is RS, one RC, right? So if R is less than RC, what's the average amplitude and throughput? RS, right? It's smaller. Okay. If RS is larger than RC, what's the end amplitude throughput? It's RC. Okay. It's always just follows the link with the narrowest bandwidth. Okay. So you know, this bottleneck link, right? This smallest bandwidth link is where it decides the speed. Okay. So this is the takeaway message, right? But will this cause a problem? Oftentimes it will not, right? So if it's in the middle of your routing path, that will cause a problem, okay, for sure. But you think about it, as we just described, okay? If, let's say, you have some intermediate router serving a lot of other regional router, maybe this is a continental router, right? We will over budget the rate, right? So what if you remember LA divided by R, right? We will over budget this R, right? We will over deploy this R to be much larger than the summation of the R's. Okay, so then there will be no queuing delay, right? So usually the actual bottleneck is often the first link or the last link from your end to the ISP or to the destination. Okay, so this is called the per connection end-to-end throughput, right? So here we have, for example, from these computers, these servers and stuff to the computers, right? This is a client rate, this is server rate, and assume we use some fair protocol like TCP, right? They will back off until finally everyone will consume only let's say we have 10 machines, right? So everyone will just consume 1/10 of the bandwidth. Okay, initially maybe not, but the TCP protocol will guarantee the fairness finally. Okay, after back off and adjusting. So as we said, in practice, often these end links at the bottom, this will be over budgeted, okay, over deployed to avoid the queuing delay. So that should be fine. Okay. Yeah, so that's basically the end of this slide. Any questions? If not, so we will continue. So I think we have already. I think we have already got one lab or two labs. Can anyone remind me?
We have done only one lab.
One lab, right? So the next lab will still be, packet tracer. But from the third lab, what we will do is we will do the socket programming. Okay, so for that reason, we need to go through the socket programming a little bit. Okay, there's a tutorial. There's a textbook I like a lot. Actually, I would recommend that for sure. So that's let me see. Let's get a new window. So, but we are following a different. Yeah, we will have a. I think I received a question. Okay, yeah, we will have a quiz on these math questions. But as long as you get a hold of this concept we described today, it should be not difficult. Okay, it's just after you take a slide, then you immediately get some tests on this slide to help you memorize this concept. Okay, and so there's a top-down approach, networking. Okay, so this textbook, if you look at, so there's a free PDF somewhere. So I think it's the previous version. I'm not sure whether it's legitimate, but someone in Greece shared it, for example. Right? So then we can use it if it's still there. Right? So you can download and save and use it. Right. So, but maybe they have the copyright. I don't know. Okay, but you can get it from the internet. Right. So, and when we talk about socket, we are talking about the C socket. Right. So, but there's a particular chapter on Python socket. Okay, so like they use a top-down approach, application layer down. Okay, so there's the Python socket programming section 2.7, right? Let me put this link maybe to the chat so that if you want it, you can get it. Okay. I strongly recommend you to read this subsection. Okay, we don't require you to read a lot of the textbook, right? As long as you understand slides, but this one I strongly recommend you to read. Okay, it's very detailed on socket programming. It tells you everything bit by bit, UDP and TCP, okay, and then sample code and what each code means, right? So basically, after you go through these stuff, you will understand how to code, right? So we will talk about something similar, but in C code, C API, because even Python API, it's based on the C socket, okay, C socket API, right? So we will describe a little bit as a lower level, but when you program, probably you just want to use Python. I understand a lot of, I think our undergraduate program is teaching Python as a programming language, right? At least for the first course, maybe 103. Right? So maybe if you are more familiar with Python, you can use okay.
So just to clarify, we use Python for the assignments in this class?
You can use any language.
Okay.
But I mean, most of you, maybe especially undergraduate students, are more familiar with Python than C, right? So if you want to go through the Python API, so that's section 2.7. I just look at these maybe 5 to maybe 10 pages. But if you look at the layout of this, each page is really small. Right? So if you read this, it will tell you basically everything. Okay, that you need to know. I put the link already on the chat, so then you can just read it. Okay. JavaScript, I'm not sure. So you need to have the API, you need to have the library, right? I never check whether JavaScript has the API for for socket programming. Okay, but I know that the Java C, Python, they all have this API. Okay, because for me, oh sorry, did I send? Yeah, I sent the link to everyone. Okay, so yeah, so for me, JavaScript is really a local running program, right? So for changing your layout of your your web page, okay? But these days we also have the server end, so maybe like node.js, right? So maybe they have the structured programming library internally, but I'm not that familiar with JavaScript for the network communication part. I'm only familiar maybe with like DOM processing part, so I cannot answer that question. Okay. Yeah, so I see somebody already answered this question, right? So I'm a little bit outdated, right? I use, for example, Java server page, right? Now people use Node.js, right? So I didn't update that knowledge, okay? So I think that could be this API, you can use that if they're equivalent, okay? Any language is fine, as long as you can demo that things are done, right? Let me see the, yeah, which slide? Okay, so here we are talking about C socket. It's really C language socket, okay? Oh, I see. I see some students have like a signal issues, right? So we will release this video on YouTube. Okay, so I will send the link after the class, so you will be able to see. So let's finish a few slides, and then because there's only 3 minutes. Okay. I probably will not take attendance for this class. Maybe for the next, I will take attendance. Yeah. So the goal, why we need to talk about socket programming, right? So again, why we talk about C, right? Because C is a foundation. C socket is a foundation of every socket. Every others are just following the same API. Some are just wrapping the C API. Maybe I think Python's API is just wrapping the C API. Okay, so C socket are the de facto standard for network APIs. It's established first. C is a very ancient language. Okay, right. So so you will see the first programming project, but we will not release it right now. We will definitely release it after the next lab, okay? Because we don't want to have overlap of hands-on stuff with you guys, okay? So there will be a server setup for you, right? Using TCP protocol, okay? And you can write your client to interact with the server according to what we requested in the assignment, okay? You can use whatever language you want, okay? Socket exists in almost all of them, okay? Right? But we will just describe C API here, okay? So the socket API initially is very early, right? Last century. Okay, initially called Berkeley sockets, right? Then the BSD, right? B means Berkeley, right? BSD sockets. And it then goes to Unix, and then POSIX. POSIX is more broader than Unix, right? Linux is also following the POSIX standard. Okay, right? And this is also the origin for TCP/IP. Okay, all other socket APIs are based on C sockets. Right? Basically, it's a wrapper of C sockets. And I think I will stop here, and we will look at a little bit more on the project, like client server mode. But again, socket is really low-level stuff, right? You write on TCP UDP. Okay, I want to take maybe 1 more minute to describe something else. Okay. So you can, so there's some higher end APIs than socket. Okay. If you are working on distributed systems, there's socket, so zero message queue, say MQ, and you can see there's difference between them and socket, right? So there's a story on that. Why I have socket, why I use zero message queue, right? So this is another socket API, but a lot more user friendly. If you have interest, you can look at zero message queue. And there's also, MPI for communication, a message passing interface. Okay, so socket is really the low level. Okay, so but we will talk about it. Okay, that's pretty much end for this class. We will continue with the socket API and the introduction next time, which will be on the C API. Okay, you can look at Python API following the link I sent. Okay, and section 2.7. All right, so that will be the end of the class. Any questions?
Yes, I have a question. You were breaking up really bad when you was discussing the assignment part of it, and you said working with Python. I didn't get any of that.
Oh, so okay, so one question is: everyone experiences this, or it's just one student? Yeah, if another student.
I had a problem. I just disconnected and connect back to the meeting. It was okay now.
Oh, I see. Yeah, so we will share the video. Okay, you can rewatch. Okay, on YouTube. But for the assignment, we are talking about using Python or C. It's basically the socket programming. We will continue next class. I will repeat that. Okay, so no worry if you don't get it. And you can also watch the last part of the video. You will get it. Do you answer your question, Rachel?
Yes.
I think not Rachel, right? So some other student, right? So maybe I see the wrong name. Okay.
It was Banka.
Oh, okay. Any other questions? Yeah, if you have no question, feel free to leave. Okay, if you have any questions, just mute and ask. I will be here for 1 more minute. If there's no more questions, then I will leave. Thank you. Have a good day.
So Dr. Yan,
Yes.
you said that you assigned our project. Are you talking about the group project with only 2 people?
Yeah, there will be a group project. That's a group project. But we haven't released it yet. We are teaching what you need to know before working on the project. Yeah, right now.
Okay, but
Yeah.
it's not, because I know we have like a week to do the projects as soon as they're assigned. You're not assigning it today, right?
No, I will assign to maybe next week. Okay, so because
Okay.
you still have the lab, etc. Right. I'm teaching it first, then you will be able to handle that. Okay.
Okay, no worries. Just trying to keep up. Thank you.
You're welcome. Any other questions? Okay, so then I will disconnect. And if you have any questions, feel free to send email to me. Oh, I see some chat. Let me see. Okay. I will release a quiz today. Okay, so next quiz again will be 2 weeks. Okay, so no worry, you can finish in anytime in 2 weeks, right? And if you understand well, you can, yeah, you can finish even today. Okay, right. I will see you guys, and I will send the video. Maybe it's you know, there's some signal issue. Maybe if it's on my first hop link, right? So then there will be some issue. Okay, I will send the video. I didn't take attendance today. Okay, I will not take attendance every class, but I will take attendance almost every week. Okay, because if attendance takes some time, right? Okay, then I will see you next class.